Welcome back to the workshop for a brief discussion on definite integration. Now, definite integration is presented as a way of calculating area below curves or between curves or endless applications. So we want to just really take a quick look at not the development like we did in differentiation, but just the fundamental theorem of calculus, which really nicely gives us a way of calculating definite integrals rather than that limit process in the development of definite integration. So let's take a look at our notes a moment. So the fundamental theorem of calculus says that the definite integral, right, if we're talking about the area underneath a curve from A to B, right, this is one interpretation of it. This isn't a definition, but we have the definite integral from A to B of f is the antiderivative evaluated at B minus the antiderivative evaluated at A. Fundamental theorem of calculus. So, and again, a nice interpretation is that gives us the area between the curve and the x-axis from A to B. So let's take a look at evaluating this definite integral here. All right. Let's see, a couple different ways that we could approach this. For sine of x times cosine of x. This actually looks really similar to what we took a look at in our previous video, integral of sine times cosine. In the last one, cosine was, or sine was raised to a power. And I think I'd like to make essentially that same substitution. So this is a little bit weird. All right, let u be equal to sine of x. Then du is equal to cosine of x dx. But because it's a definite integral, we also have to replace the integration bounds if we're going to do this completely and thoroughly using the substitution technique. So if x is equal to pi over 4, then, well, plug pi over 4 in. U is equal to sine of pi over 4, which is square root 2 over 2. And if x is equal to 0, then u, which is the sine of 0, would be equal to, sine is the opposite side at 0. So that's 0 here. So we can observe this as 4 times the integral from 0 to pi over 4 of sine of x times cosine of x dx. So we can see u and du. So this is 4 times the integral from 0 to root 2 over 2, and u times du. Pretty easy here. Integral of u is 1/2 u squared. So this is 4 times 1/2 u squared evaluated from 0 to root 2 over 2. So this notation says we evaluate this function, right? This is the antiderivative, evaluate it at root 2 over 2, and then subtract evaluation at 0. So this is 4 times 1/2 is simply 2. So this is 2 times root 2 over 2 squared minus, right, that's the evaluation here, 2 times 0 squared. So this thing squared, so 2 times square root of 2 squared is going to be 2. 2 squared is 4 minus 0. And we get that the area is 2 times 1/2 is 1. Cool. So that's an example of a definite integral. There's a practice problem for you to take a look at. That one should not be too bad, right? There's a composition there. You should be able to see that, perform a substitution. And let's see here. Yep. Should be able to do that. And then there's one more comment, just the second fundamental theorem of calculus, the derivative of an integral gives us back the original function. So feel free to take a look at that. We may end up using that a little bit this semester, but it's worth including, but I didn't figure it was worth really spending a lot of time discussing. All right, so that's it for our review on differentiation and integration. Thank you for your time. I will see you guys back in the workshop, back in the classroom a little bit later. Have a great day.